Within this video, I provide feedback for a practice task that included questions from Chapter 1. Here are the 7 questions that I'm going to go over. First question, ask what information is most useful to describe the precision of measured values. As a test taker, I see the word precision, and I want to think about what that means before I read any of the choices. Sometimes different choices on a question, they can sound awfully compelling, awfully good. So before I begin to address that and evaluate them, I want to pause and think about, what do I already know about precision? I'm thinking about that we can describe data in terms of both their precision and their accuracy, and these are different things. As shown within this representation for a dartboard, we can have examples with both good precision and good accuracy, or examples where the accuracy is quite poor. They're not in the center of the target, but they're in a very narrow range. That idea of being in a narrow range, that's what I'm thinking of when I'm going to evaluate the precision of the measurements. Another important detail found in the e-text is that precision and accuracy don't always go hand in hand. You can have a measurement that would be quite precise, but have poor accuracy at the same time. Looking at this one, how might this show up on a test? A good thing to try is to change the question. What if this question was in terms of accuracy? How would you answer it then? You can also find examples within the e-text involving analyzing data. So I'd say these are other ways that you could expect the same topic to be found on an exam. Question number 2, I'm seeing particle representations, and in this case it says we're going to begin with an element and a compound, look for a chemical reaction, and then have the products be a mixture of an element and a compound. So to answer this question, first thing I want to recall, it's important to know that a compound consists of 2 or more different elements. So in this picture right here, I see that we have the elements being shown paired up as the filled spheres, and the compound being the combination of 2 different types of elements. That first example, I like the way that I see a mixture of an element and a compound being formed, but it doesn't meet the other requirement of being a chemical reaction. This is not a chemical reaction. It looks like the element that began as filled spheres was initially a solid and became a gas. I don't see a chemical change taking place. The second selection, okay, this now is a chemical change. There's an element, which are the filled spheres, and a compound beginning as a reactant. It produced a different element, which were the open spheres, and a different compound. So I like that one as the answer. It's helpful to consider why choices C and D are not correct. They're both chemical changes, but they aren't meeting the requirement of having an element and a compound undergo a chemical reaction and produce a mixture of an element and a compound. So it's always helpful within this to consider, as another one, can you change the question so an incorrect response is correct? For both C and D, I talk through what was taking place, or I show what's taking place right here. If the question had been asked differently, any of these could be correct, A, B, C, or D. So it points out that we got to be careful with the chemical language that we're using, the vocabulary, and what we're looking for within the representations. In the text, you'll find other examples of connecting the language, things like mixture, element, compound, chemical change, physical change, with particle level representations. I would also put in the same category these types of questions where some everyday object is listed like sand or air, and it's being asked, is this a pure substance? Is it a mixture? Is it homogeneous, heterogeneous? All of this is using vocabulary that we find describing matter. Let's look at this one. The kinetic energy of an object is calculated using the formula 1/2 mv squared, and it often has units of joules. What is the kinetic energy? So the first thing I'm going to do is I'm going to pause and make sense of the provided equations. Kinetic energy is 1/2 mv squared. And if I'm going to have it in units of joules, a joule is defined as a kilogram meter squared per second squared. So the mass that I would be using in 1/2 mv squared, the mass would be in kilograms. The velocity would be in meters per second. If I take the meters per second and square that, that becomes meters squared per second squared. So this is how it's fitting together. So I see within this I have to convert then grams to kilograms and miles per hour to meters per second. The first one, grams to kilograms, that's an easy conversion. The second, miles per hour to meters per second, this is going to be longer and we'll make use of dimensional analysis. Let's start out then with what we know and finish with what we want to know, what we're going to try to figure out. We have a value in miles per hour, and we need to convert that to meters per second. So let's start by changing miles to meters. I can convert miles to feet. That was provided within the question. I can go feet to inches. An important conversion is the definition that 1 inch is 2.54 centimeters. And then if I go from centimeters to meters, I've taken it and now I have my distance in meters. Converting my time, 1 hour is 60 minutes, and I have 60 seconds in every minute. This gets me to meters per second. I now have a value for the mass, a value for the velocity. So let's plug them into the equation 1/2 mv squared. Plug that into the equation and I will get it reported in kilograms, meters squared per second squared, and that's in joules. The most common student error on this question would be failing to include the value of 1/2 that was found in the 1/2 mv squared. Students would actually have more success working through the dimensional analysis than attending to that particular detail. So we need to be careful with any information that we have. Now, if we look at this work solution here, what information did the problem solver need to know? Given the equation, what did we need to bring into the problem in order to solve it? Well, we had several examples of metric conversions. We had examples involving time conversions. And we crucially had this link of 2.54 centimeters being defined as 1 inch. Beyond that, we had the skill of dimensional analysis that we were applying. Perform the calculation and report the answer with the correct number of significant figures. So I'm going to be alerting myself right away. Okay, this is a mixed operation significant figure calculation. Mixed operation means I've got addition and subtraction, and I also have division. As soon as I have examples with addition or subtraction, I want to be extra careful with those. I want to be able to stack them up and consider where they are aligned with their decimal points. Within this one, I also see that I have different units for length, meters and centimeters, and I have something listed in scientific notation. So this is how I would go about it. I'd begin by taking the expression with scientific notation, get it out of the scientific notation and convert it to meters. And then I want to stack up my addition and subtraction. So when I'm doing the subtraction, I'm stacking it up over the decimal point, and I see that this will be good reported to 2 digits after the decimal point. When I do the addition, I'm going to stack them up, and I see that that's also reported good to 2 digits after the decimal point. So that means that the first one on the left here has a total of 2 significant figures when it's involved in a multiplication or division, and the one on the right involves 4 significant figures. Key step in here is that stacking it up when I'm doing addition or subtraction, because with an addition and subtraction, remember that's not the same rule as multiplication or division. Then when I work through, I see I have a value with 2 significant figures, 4 significant figures. Can take the whole thing and then round it at the end. You'll find within the textbook examples where you're asked to indicate the number of significant figures. That's a fine initial skill, but I know our objective is to perform calculations like these. Perform calculations that are mixed operation that will include the rules for addition and subtraction and also include the rules for multiplication and division. Here's a description of a cube that has a density of a particular value, a mass. We're asked to report the length. So right away what I'm thinking about this is, okay, a three-dimensional object, its volume would be length times width times height. And for a cube, all of these sides are going to be equal length. Second is my definition for density is mass divided by volume. Mass divided by volume. Density equals mass divided by volume. In this question, I have 2 out of 3 of these terms. I see that the density is listed. I see a mass is listed, but not the volume. If I can get to the volume, I can use that to determine the length. So let's do some simple algebra here. Density equals mass divided by volume. If I bring the volume and multiply it by the left-hand side, it would be density times volume equals the mass. And then bring the density over from the left to the right would lead me to have the mass divided by the density is equal to the volume. So let's just do that calculation. I have a mass term. I'll set it up so that when I multiply through, the density now will cancel, and I'll figure out in cubic units what would be the volume of the cube. Cubic units means length times width times height, or side times side times side equals that particular volume. So I can then take the cubic root of that, which would also be raising it to the 1/3 power on my calculator, to find out what is the length of each side. That last part, be sure you could do something like that on your calculator. Okay? Can you take the cubic root of something or raise it to the 1/3 power? Make sure you have that skill. Now, what did the problem solver need to know in order to answer this question? They certainly needed to know the definition of density and the volume of a cube, and how to go from the volume of a cube to the length of one of the sides. And then finally, some simple algebra was involved. Now, when I say simple algebra, manipulations like this, where we have, let's say, 2 out of 3 terms, or 3 out of 4 terms, and we have to perhaps switch them around to solve for our missing one, these are going to be really common throughout general chemistry. Here's some end of chapter questions. These are all involving density, but notice they're not simply saying plug something in and calculate the density. Oftentimes they're listed as scenarios. I think within each of these, if I saw the word density within the question, I would pause, I would write what my definition for that is, and then I would begin to see how is that applicable for the scenario. In this one, it's describing a distillation experiment. Now notice the format. We have 2 different statements and we're asked to identify which combination of them are true. So this is really a question that has 2 true or false statements that we're evaluating. A distillation experiment in which a saltwater solution is heated. Within our e-text, we find a description for the separation of mixtures. 3 different approaches are described: filtration, distillation, and chromatography. A closer look on the distillation. It's stated that this is an important method for separating the components of a homogeneous mixture, and it depends on the different abilities of substances to form gases. In this particular scenario, if we begin with salt water, we would indeed produce 2 pure substances. The salt would be left behind, and the pure water, which would be formed and collected in the receiving flask, that's another pure substance. So I like that statement as being true. The first one, the initial solution is a heterogeneous mixture. I like that it's a mixture, but I would say it's a homogeneous mixture. The initial salt water is, the salt is distributed throughout. If it's distributed throughout, then we have a homogeneous mixture, not a heterogeneous one. So in my reading here, I think only statement 2 is true. My suggestion for this, review the section on the separation of mixtures. Filtration, distillation, and chromatography are all discussed. Try to describe each of those in your own words, And then you can try a self-assessment question that you'll find within the e-text. Final question, which of these is an intensive property? This would be another example where I would not look at the answers and I would pause and ask myself, what is an intensive property? We find that some properties, such as temperature and melting point, are intensive. They do not depend on the amount of sample being examined. In contrast, an extensive property depends on the amount of sample that you have. I like this inclusion where it says many intensive properties can be used to identify substances. Density would be an example, right? If you were able to measure the density, you could distinguish between the metals being aluminum or copper. Now, if I look at these choices right here, I don't think any of these allow me to identify the substance. Mass, volume, temperature, or length, I could have all of those vary without having it allow me to gain insight into whether is it a piece of aluminum or is it a piece of copper. So I like this description, how many intensive properties can be used to identify substances, but not all of them. Within that set, which of these depend on the amount of matter present? If the object is bigger, its mass would be bigger. If the object is bigger, its volume would be bigger. If the object is bigger, the length would be bigger. But if the object is bigger, the temperature does not necessarily have to change. So I like temperature as being an intensive property, and the other ones as being extensive. Now notice within the format of this question, you could ask, what is an intensive property, and look for the definition of it? Or, which of these is an example of an intensive property? On your exam, you're going to find examples that are applications, questions that are applications. We almost never have a question that will be, what is the correct definition? It's almost always taking the definition and then applying it in some way to a scenario. So in summary, the topics and questions within this video, they're all aligned with objectives from the textbook. That tells me two different things. One is the textbook is a great resource for finding the content that can be on our exam. And second, everything that was discussed within the video here are all very legitimate questions, topics that you could find on your test. On an exam, I'd predict that the questions involving calculations would probably score lower than the questions without calculations. If I had to predict, the question involving the significant figure calculation would probably be the lowest scoring amongst the ones discussed here. So it's up to you now to self-assess. Have you mastered all of these topics? Could you explain each of these topics to a classmate? Can you answer other questions on these topics as well? If you identify any weakness, be your own harshest critic here. Self-assess, and if you identify any weaknesses, now is the time to address them. Don't wait to improve your understanding. The course will be moving on to many new ideas. Now's the time to master the ones discussed here.